Rime ice is formed when small, supercooled water droplets freeze rapidly on contact with a sub-zero surface. It appears white in color when viewed from a distance, for example from the flight deck when on a wing. Since rime ice forms on leading edges, it can affect the aerodynamic characteristics of both wings and horizontal stabilizers, as well as restricting engine air inlets. Rime ice can be removed by the de-icing systems under normal conditions without any problems. Airframe contamination cannot only occur when precipitation is present. Snow, ice and other deposits may be lifted by the force of strong winds and the jet blast for maneuvering aircraft and might be deposited on aircraft surfaces. Water system will be affected by temperatures below freezing. Correct procedures for draining or refilling must be followed. A thorough and vigilant pre-flight inspection of the engines is required during cold weather operations. Operators equipped with engine cowl covers and inlet plugs should use them to protect from ice, sleet and snow contamination. While the use of covers and plugs is recommended, this equipment does not totally eliminate contamination of the engine inlet. Anti-ice systems shall be activated as per the manufacturer or operator procedures. Aquaplaning, also known as hydroplaning, is a condition in which standing water, slush or snow causes the moving wheel of an aircraft to lose contact with the load-bearing surface on which it is rolling, with the result that braking action in the wheel is not effective in reducing the ground speed of the aircraft. In the case of the most common type of aquaplaning, called dynamic aquaplaning, a simple formula exists for calculating the minimum ground speed for initiation of this type of aquaplaning on a sufficiently wet runway based upon tire pressure, where V equals ground speed in knots and P equals tire inflation pressure in psi. V equals 9 times the square root of P. Some inspected areas can be cleaned manually during the inspection and a de-icing procedure is not necessary. This procedure must be confirmed with the flight crew. The captain has the final authority of the procedure, but the safe option should always be considered, whether it is the opinion of the flight crew or ground crew, company and aircraft limits to be noted. There are some areas to include in the inspection while waiting for instructions from the flight crew. Areas to check include wings, upper and lower, vertical and horizontal tail surfaces, fuselage, propellers, engine inlets and fan blades control surfaces and gaps, pitot heads and static ports, landing gear and landing gear doors, antennas and sensors and all other aerodynamic surfaces. After checking these areas, a decision with the flight crew of de-icing procedures can be made accordingly. The weather elements and taxi distances will affect the choice for type and mixture of fluid to use. The color of Type 3 fluid is yellow. The purpose of this fluid is to give a reasonable protection compared to Type 1 from refreezing. With the lower viscosity of this fluid compared to Type 2 and 4, it is better suited for regional airplanes with lower takeoff speed, under 85 knots, or for airplanes with other restrictions on thickened fluids. Type 3 fluid may have a different lowest usable outside air temperature. The application limit may be lower, provided a 7 degrees Celsius buffer is maintained between the freezing point of the neat fluid and outside temperature. In this case, a pre-takeoff check should be performed. The commander shall assess, prior to takeoff, whether the applied holdover time is still appropriate and or if untreated surfaces may have become contaminated. This check is normally performed from inside the flight deck as a visual check. It is extremely important not to confuse tailplane stall with wing stall, since recovery actions are exactly opposite. In tailplane stall, the flaps must be decreased and the yoke must be pulled full aft. In wing stall and roll upset, yoke must be pushed forward. Remember that since in tail icing conditions, a reduced flap setting is required, a higher velocity and, as a consequence, a longer landing field length could be required. An approach to land on a contaminated runway requires a fully stabilized final approach and a firm but not hard touchdown within the prescribed touchdown zone. If either is not achieved, a go-around or rejected landing is appropriate. The challenges of achieving a successful contaminated runway landing are such that there should be no indecision in either case.